This is Sholey Physics episode on scalar products and finding the angles between vectors. Hopefully you've learned how to add vectors like vectors A and B you might see here. But what about multiplying vectors? What is that? So adding vectors looks like, something like this. Vector A plus vector B gives you a resultant vector C. That's adding them. But what if we wanted to multiply A times B, vector A times vector B? What is that? There's two ways to look at it. We can multiply the parallel components of A and B or the perpendicular components. We kind of have to choose. Now, if we multiply parallel components in this to find A and B, there's a little problem here. There is no parallel component of B. So the result of that would be 0, and that would be called the scalar product. Now, what if we multiplied the perpendicular components of A and B? A and B are both exactly perpendicular with one another. So let's get into a situation where A has both parallel and perpendicular components to B. Now we can start looking at both. We could find the horizontal or the perpendicular component and compare that with B, or we could find the parallel. A goes down into the right in that little situation I just made up. So there might be a vertical component here. We'll call that A in the y direction. All right. What if we can multiply that with the downward B vector? Okay. Now there's a physical scenario where this might crop up. What if you've got a box on a plane and you're giving a push with a force, some kind of force here? Now you're going to move it in this direction to the right. Now that force has a horizontal component to it and a vertical component. Now if you push down on a box, it doesn't go anywhere. So in this case, the perpendicular components of the downward component, the downward force, and the sideways motion of the moving box, they're going to cancel. There's going to be no result of that. So the perpendicular components, this downward component and the horizontal motion, won't give you any result. However, we might focus now on these parallel components. You see, this force isn't just pushing down, it's also pushing over as the box moves over in this direction. So is there going to be some kind of physical quantity that results from that? And the answer is yes. When we look into work with forces and displacement, that'll crop up here. This amount of force in the horizontal direction will have an impact along with that displacement of the box and something called quantity called work. So you'd have to multiply the component of the horizontal component of force with the displacement to get work. So what if I were to try to find the product of A and B, these two vectors? A, first off, just get a visual. A is 2i minus 4j. So that's like a vector that has 2 units in the x direction and 4 units in the y direction. So that's a vector that looks a little something like this. All right, if this were our origin. And vector B, let me label vector A. Vector B is negative I minus 6j. So negative I would be a negative 1 in the x direction and minus 6 in the y direction. All right, so that would be a vector that looks a little something like this. There's A and B. So what is A times B? That's the big question. We'd have to either take the parallel or the perpendicular. We'd either have to take the parallel or the perpendicular components. So in this lesson, we're going to be looking at the scalar product. In the scalar product, you take the parallel components or the anti-parallel. So that means the components out in the same direction or opposite directions, and I can't spell components. There we go. So scalar is the parallel components. Therefore, the i's will be multiplied. But whenever you've got an I times a j, that's going to be ignored. Mathematically, what does keeping and ignoring look like? Well, definition of a scalar product of two like directions, let's say I dot I. By definition, I dot I is going to be 1. Now, I said dot here, that's some terminology referring to the scalar product, as opposed to what we'll see later if we take a cross product. Okay, that'll be something different later on. So this is referred to the cross product, and in conversation we would say the dot product. All right, so dot and cross. So we have this definition, I dot I equals 1. Well, what would I dot j be? I and j refer to the x and y directions, and they are completely perpendicular to each other. They're 90 degrees with one another. So by definition of the scalar product, we're going to ignore those perpendicular components. That means I dot j is 0. So keep that in mind. If we do get into a third dimension with k, and I'll also keep in mind that I dot k would be 0 as well. X direction is perpendicular to the z direction as well. And we can also assume that j dot j would be 1 and k dot k would also be 1. If you ever have a component of a vector that's in the same direction as a component of another vector, you will multiply those. You'll take the scalar product of those two and keep it. And just keep in mind, any number times 1 is that number. So the directions either allow a product to be kept, or they will cancel that product, that component of the product. All right. So if we look at A and B, what we're going to be doing when we take the scalar product of A dot B, I'll write that out. This is our big question. What is A dot B equal? What's the result? That is not a new symbol. That is just a bad marking. Okay, that's our little vector symbol there. All right, so what would this be looking like? Well, we're going to be taking the horizontal component of A, this blue one, and the horizontal component of B, and multiplying those together. And then we'll also have two vertical components that will multiply together. Okay, so those two on the outside will multiply, and these two on the horizontal side will multiply. But what about this component and this component? Remember, those are A dot j. So those two components will not have a bearing on the scalar product. All right. So when we take any two defined, let's say, algebraic expressions, like A equals 2x minus 4y, and we take B equals negative x minus 6y, if you multiplied those two together, like A times B, that would be like a 2x minus 4y quantity times negative x minus 6y as a quantity. So in the same way, A dot B is going to look the same way in an algebraic expression. 2i minus 4j dot negative I minus 6j. All right, and we're going to distribute, use the distributive rule the same kind of way. 2i dot negative I plus 2i dot negative 6j, and in my algebra class, this is my algebra 1 class, this is kind of the thing we did. Multiply out there, distribute, and then add these two distributive products. All right, so that's the flow of what's going to happen here. So 2i dot negative I, what is that? Well, 2 times 1 is 2. And I dot negative I is negative 1. Remember, I dot I is 1, so I dot negative I is negative 1. Okay, I like to put that out there. My calculus class, I ended up with high B's on all my tests because I messed up the negative. So let's keep it keep it clean here. Make sure we get all those negatives correct. Now we're going to take 2i dot negative 6j. So I got 2 times negative 6 is a negative 12. I'm handling these negatives a couple different ways. Just go with the flow as long as you account for them. So I did 2 times negative 6 is negative 12. Now what about I dot j? I dot j is 0. 0. So this whole term is nullified. We're not going to multiply the j components. Now we've got, we're going to go to the second term here, negative 4j dot negative I. So negative 4 times negative 1 is a positive 4. Didn't really need to put that in parentheses. And then j dot I, again, those are perpendicular components. J dot I is going to be 0 also. That is a 0 nullified portion of our answer here. And finally, we've got negative 4j dot negative 6j. So negative 4 times negative 6 is positive 24. And j dot j, just like I dot I, j dot j is 1. So this is 24 times 1. In essence, we're keeping the 24. We're keeping the negative 2 over here. And we're throwing away all the I dot j components. So to simplify, we've got a negative 2 plus 24. The scalar product is, you guessed it, positive 22. It's not 22i, it's not 22j, it is just 22. And that's why this is called a scalar product. I had a technical glitch there. Scalar product, because there is no direction to this answer. This is just a scalar value. There's no north, east, south, west, up, down, x, y, z. There's no direction to this answer. It is just 22. That is the scalar product. Okay, and that's how you work it through. Now I think instead of distributing, doing all this stuff, is a slightly easier way using the eyeball. If you stack your two vectors that you're multiplying together, look how easy this is. 2i dot negative I is negative 2. And negative 4j dot negative 6j is negative 4 times negative 6 is 24, and j dot j is 1. So there we go. It's a lot easier to do if you just stack them and work it with your eye, because the I dot j and j dot I, those cancel. Those pieces are 0. They have no bearing on the solution. Okay, so that's the scalar product. It's how you work it. So let's talk about what that is. What does it look like here? Well, if we go back to one of my earlier scenarios, pushing a box, all right? There's a force, and it's going to displace the box to the right. I'll call that x. Okay. Actually, I'll call it delta x because that's what a displacement is. All right. And let's say there's an angle for this force. I'll just call it theta. Keep it generic. All right. So if we multiply f and x in this more physical situation in the physical real universe realm, what we're going to be multiplying together are the parallel components of f and x, f and delta x. So when you push a box, it's going to go along the floor. Any of the downward push is going to be canceled, aka I dot j equals 0. And any of the pushing force that goes in the same direction as the displacement is going to be multiplied by 1. It's going to count, aka I dot I equals 1. So when we take f, the vector f dot delta x, all right, this is like an a dot b. What is the result going to be? Well, the result is going to be the product of the two parallel components. Well, delta x is horizontal, and there is a horizontal component to f. So if we find that horizontal component of f, we're going to be able to multiply that by x to get our solution. So this component, if we make a little triangle here, a right triangle, you'll notice that this component is adjacent to the angle theta. Therefore, it will have a magnitude of f cosine theta. The cosine goes with the adjacent side, f cosine theta. So the result here will be f cosine theta times delta x. That should be our result. Now if we reorder this, we get f delta x times cosine theta. Now through this example, I'm giving you the definition of a dot product in terms of the magnitude of each vector. We'll go with the different color here. We've got the magnitude of each vector, f and delta x, times the cosine of what? The cosine of the angle between them. You see this angle up here would relate to an angle down here, if that were f. Okay, they're the same exact angle. And that's the angle between them. Actually, f would be kind of more like this if x extended out there. All those angles are the same. So to define all this, I'm going to put it nice and big at the bottom. If we take A dot B, we would get the magnitude of A. And in vector notation, if you put these bars around a vector, it means the magnitude of. It's kind of like the absolute value, if you want to think about it like that. So the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. And that is a definition of a dot product. Oh, that is just lousy. Okay, let me just scroll through that. You know what? I got this neat box over here. Let me use that neat box. Like boxes. There we go. Some new vectors drawn out. A new vector A. And let's say it's 20 units long and an angle of 45 degrees. Okay. And let's take a short vector B. Just want to show you how this works. And we'll make this one 15 units long. There it is. So according to this, I think you can see that the angle between them should be a clean 135 degrees. It's the 90 right angle there plus 45. So our angle between them is 135. Okay. Now let's first take A dot B. What is that going to be? Well, vector B doesn't have any horizontal component to it. So really what we're going to be multiplying here for A dot B would be this component of A. All right, so if this is 45, this is also 45 in there. So we would have A cosine 45 as that component. A dot B will be A cos 45 times vector B. Filling in some numbers, 20 is the magnitude of A. I'm going to bring the B over here to be next to the A. 15 is the length of vector B, and cosine of 45. Okay. Now, you might take a note that cosine of 45 is equal to the cosine of 135. So, just as easily, this angle can be used as well as 45 degrees. So that would be also equal to our definition up here. Take the magnitude of A times the magnitude of B times the cosine of the angle between them, just to show you that this rule works just fine. Now, what if these were in IJK format? What would that look like? Well, vector A would have to define a little bit here. Let me turn on my calculator. A has two components to it. It goes up and over, and the angle between them is 45. So the up component, 20 cosine 45 is 14.14. And likewise, because it's a 45-degree angle, the horizontal side, the A sine 45, would also be 14.14. So let me put a 14.1, I'll keep it at that, I plus 14.1 J. That would be our vector A. And vector B is only in the y direction, but it's in the negative y direction with a magnitude of 15. So that one will be negative 15J, just to interpret it into the IJ context. All right. So what is A dot B then? Well, let's go back to what we were doing up at the top. Just take a look at what that was all about. We're going to be, we've just stacked the two new vectors, and I'm going to multiply the I components and the j components, and I'm going to ignore the I dot j's altogether. So what we're going to have here. So 14.1 I dot negative 15j is 0, so we're going to ignore that component and move over to this one, 14.1 j dot negative 15j. I'm going to multiply those together, 15 times negative 14.1, and we get negative 211.5. Okay, so that's A dot B, negative 211.5. So what if we were just given these two vectors, and that's it, and you're asked to find the angle between them? All right, what can you do with that? Well, we can find the dot product. It's right there. But what we'd also have to know is, get back our definition here. If we know the dot product and we know the magnitude of A and B, then can't we figure out what the angle is going to be with the inverse cosine? So that's the formula here for figuring out the angle between two vectors. If you have A and B defined, as we see here, what's the angle between them? So first you find the dot product, put that as step 1. Step 2, what's the magnitude of each one? Well, the magnitude of A, if I do 14.1 squared plus 14.1 squared and take the square root, I'm going to get the hypotenuse. Now we can already see that it's 20. So the magnitude is 20. And the magnitude of B is 15. Notice I'm not putting any positives or negatives. These are just the magnitudes, like the absolute values, the amounts. And finally, step 3, if A dot B equals magnitude A times B cosine theta, then doesn't it show that cosine theta would be A dot B over magnitude A times B? All right, just take a look at that in your head algebraically. So the angle then would be the inverse cosine of that result. So let's check that out, see if it works. We should get 135 degrees. If I plug in a negative 211.5 for the A dot B, and then down here we're going to get 20 times 15. And try that on the calculator. So negative 211.5 divided by quantity 20 times 15. Negative 0.705. And I'm going to take the inverse cosine of my answer there, of negative 0.705. 134.8. That's really close to 135 degrees. Okay, little reverse engineering there to find that angle. So what can we do back up here? We've got two cryptic looking vectors A and B. Let's find the angle between them. All right, so what we should be able to find here is, what is this theta going to be? We'll find the angle between them. Well, A dot B, did we work that out? Yeah, A dot B is 22. So I'm going to take that. Using A dot B equals AB cosine theta, we're going to have a 22 as A dot B. That equals magnitude A. Ooh, We're not given the magnitude on this one, but the magnitude is just going to be 2 squared plus negative 4 squared. It's the hypotenuse of the x and the y components. So 2 squared plus 4 squared, and the root of that, 4.47. So go ahead and write that up there, 4.47. And then we're going to take square root of negative 1 squared, quantity, plus negative 6 squared. Keep it legit and leave those negatives in there. Of course, you don't have to on your own. So I'll take the, got in the wrong mode there, square root of, we got 1 squared, or of course that's just 1, plus 6 squared. .08. It should be just above 6 because we're adding a 36 plus 7 in there. Okay, so 6.08. So I'm going to plug in those magnitudes there. 4.47 is A, magnitude of A, times the 6.8, 0.08 is the magnitude of B, cosine of our unknown angle. So now I'm going to divide both sides by this product here, and we're going to get a inverse cosine of 22 divided by, let me go ahead and multiply those, 4.47 times 6.08, 27.2. And I'm going to go ahead and take that inverse cosine. 22 divided by my answer there. 35.95, I'll call it a clean 36 degrees. There it is. Find the area between any two vectors. Did I say area? Find the angle between any two vectors. Whoop! Beep that out there. So I hope this is instructful and helpful. I hope you have a great day.